Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. In this session, I'm going to cover how discharge is computed from the data collected by the ADCP. We're going to review the discharge computations, show how those computations are accomplished when all the data are good, and then we're going to cover what happens when data are invalid. Invalid ensembles due to invalid bottom track, invalid boat velocities due to GPS outages, and invalid depths, as well as invalid individual depth cells. Unfortunately, the ADCP is unable to measure the entire water column. At the top, the ADCP must be immersed in the water, and there is a blanking distance below the transducer where data cannot be collected. The blanking distance is the result of transducers being both the sound source and the sink. Think of a Chinese gong. When it is struck, it continues to vibrate and send out sound for a period of time. The operation of the transducers are the same. When power is sent to the transducers, they vibrate to send the sound into the water column. These transducers cannot be used to listen to the backscattered acoustic energy until the ringing or vibration has died down to a level that will not contaminate the received acoustic energy. The distance that the sound wave moves during this period is the blanking distance. The ADCP also cannot measure all the way to the stream bed. When acoustic transducers produce sound, most of the energy is transmitted in the main beam. Unfortunately, there are also side lobes that contain less energy that propagate from the transducer as well. These side lobes are not a problem in most of the water column because they are such low energy. However, when the side lobe strikes the stream bed is a good reflector of this acoustic energy, and much of the energy is reflected back to the transducer. The energy in the main beam reflected from the scatterers in the water column is relatively low compared to the energy sent out from the transducer, and the energy in the side lobe returned from the stream bed is sufficient to contaminate the energy from the main beam near the stream bed. Therefore, there is an area near the bottom that cannot be measured due to side lobe interference. As the ADCP approaches the stream banks, the depth will eventually get too shallow and the data cannot be collected. Therefore, there is also a need to estimate discharges at the edges of the cross-section. Generally, at least 2 valid depth cells are recommended at the edge before beginning a transect. The reason for this will make more sense as you understand how discharge is computed using the data from an acoustic profiler. Therefore, we have a large measured area in the center of the cross-section and 4 unmeasured areas, 1 at the top, 1 at the bottom, and 1 on each edge. Let's begin by learning how the discharge is computed for a single depth cell, or bin. The figure represents a small portion of a cross-section. The vertical lines separate the different ensembles, and the horizontal dashed lines delineate the depth cells in one of the ensembles. The dark blue vector represents the direction and speed of the water. The orange vector represents the speed and direction of the boat. The red vector is the component of the water velocity that is perpendicular to the boat vector. This is computed as the dot product of the water vector and a unit vector normal to the boat vector. D is the total depth of the ensemble. DZ is the depth cell or bin size. W is the width of the ensemble. DT is the time from the previous ping until the current ping for this ensemble. And DS is the cross-sectional area of a bin in the ensemble. Now we begin with something you all know. Q equals AV. In this case, the area is DS, which can be computed as W times DZ. How do we determine W? We know the speed of the boat and the time between pings. Thus, we can compute the width as the speed of the boat vector times the time between pings. The cross-sectional area of a single bin in a single ensemble becomes the boat speed times the time between pings times the size of the depth cell. The velocity we need to use to compute discharge is the velocity perpendicular to our cross-section. This is the velocity we compute by multiplying the water velocity times the unit normal vector of the boat vector. Therefore, discharge in a single bin can be computed as. Note, this equation contains dt, which is the time between pings. dt cannot be computed until the second ensemble has been collected and a difference can be computed. Therefore, the first ensemble always has a zero discharge because it has a zero width. Now, taking the equation we just derived, we will continue to develop it into a form that is easier to apply to the ADCP data. The dot product term can be redefined as the magnitude of the water velocity times the cosine of alpha, where alpha is the angle between the water vector and the unit normal vector to the boat velocity. Substituting theta for alpha plus 90 degrees results in the discharge equation becoming the magnitude of the water velocity and the magnitude of the boat velocity times the sine of theta times dz dt. Theta now becomes the angle between the water velocity vector and the boat velocity vector. We can now redefine the product of the boat and water speed and the sine of theta as the cross product of the water and boat velocity vectors. The cross product of the water and boat velocity vectors equals the x component of the water velocity times the y component of the boat velocity minus the y component of the water velocity times the x component of the boat velocity. This is important to remember, as we will refer back to the cross product several times in computing the discharge in the top and bottom unmeasured areas. Our refined discharge equation becomes the cross product of the water and boat velocities times dz dt. Now let's prove that this works. On the screen is some data from Wind River. We begin with the discharge equation. The first value is the velocity in the east-west direction for the water. The value is negative 4.462. Next, we get the boat velocity in the north-south direction from the bottom track tabular view. It is equal to 6.254. Then, the north-south water velocity from the velocity tabular view equal to negative 1.195, and the east-west boat velocity from the bottom track tabular view equal to negative 0.596. The bin size can be obtained from the ensemble header tab and is equal to 0.82. Delta time can be obtained from the composite tabular and is equal to 0.71. The result is the discharge in the bin of 15.83, which thankfully agrees with the discharge for the bin in Wind River 2. We have now learned how to compute the discharge in a single bin. To obtain the measured discharge in a single profile or ensemble, we simply sum the discharges in the individual bins. To compute the discharge for the entire profile or ensemble, we must include the unmeasured area at the bottom, which is a function of the bottom extrapolation method chosen by the user. We must also include the unmeasured area at the top, which is a function of the top extrapolation method chosen by the user. Then the discharge in the whole profile is simply the sum of the top, measured, and bottom discharges. The velocity profiles varies based on the roughness of the stream bed and the shape of the channel. This graph focuses on the change in profile due to stream bed roughness. The center line represents the basis for our comparison. If the stream bed is smoother, the velocity will be greater at the bottom and less at the top in order to maintain the same mean velocity. For a power curve, this means a larger exponent. If the stream bed is rougher, the velocity at the bottom will be less due to the drag of the roughness of the stream bed, and the velocity at the top will be greater, again, in order to maintain the same mean velocity. For a power curve, this means a smaller exponent. The channel width and shape can also have a substantial effect on the velocity profile. For these shapes, the maximum velocity occurs below the surface, so a standard log or power profile would not fit the data well. However, for wider streams, the maximum velocity is often at the surface and can be modeled as a log or power profile. Using the power curve in unidirectional flow conditions is very common. However, using the power fit in bidirectional flow salinity, temperature, or wind-induced flow conditions can produce erroneous results. The power curve does not fit the data at all and even predicts a bottom discharge with the wrong sign. In the past, users with bidirectional flow were forced to use a constant fit at the bottom to avoid this problem. For bidirectional flow, a piecewise fit is a better approach. All of the current software now provides this option. These are the options for top and bottom extrapolations. At the top, we can use power, constant, or a 3-point slope. At the bottom, we can use power or no slip. SonTek does provide constant at the bottom, but do not use this as we know the velocity has to go to 0 at a fixed boundary. SonTek also allows the top and bottom exponents to be set independently. However, this can produce a discontinuity in the profile and is generally not recommended. SonTek also provides the option for setting the number of bends to use. This is generally not recommended. It is recommended that when the depths near the shore become too shallow for two good bends, that the transect be stopped and the discharge in the edge estimated from the available data. So what information is available? The ADCP has the depth of the last ensemble and the velocities in the last ensemble. To ensure the accuracy of the depth and velocities, it is recommended that the boat be held in position and at least 10 ensembles collected. This will automatically be averaged in the manufacturer's software. We also have access to a value that can be measured by the user, the distance from the end of the transect to the edge of water. It is important that this distance be measured. Visual estimates are typically too short and will lead to inaccurate discharges. Now, what else do we know? First, just like the bottom, we know that the velocity has to go to 0 at the bank. Second, if we assume either a triangular or rectangular edge, we can compute the missing area using the depth from the ADCP and the distance we measure to shore. Third, we know that Q equals AV. To compute the discharge in an unmeasured edge with an assumed triangular shape, we begin with Q equal AV. We know that the area of the triangle is half the width times the depth. So for our situation, the area of the edge can be computed as the measured distance to the shore and the measured depth from the ADCP. Now we must determine the average velocity to multiply times the area. Fulford and Sauer, 1986, suggested that the neighboring velocities can be estimated by multiplying the known velocity by the ratio of the square roots of the depths at the two locations. If we now assume the midsection method normally used in the USGS stream gauging operations, we need the velocity at the center of the triangle, at L/2. Setting x to L/2 and solving for the velocity at L/2, we determine that the velocity at L/2 from the shore is 0.7071 times the last velocity measured by the ADCP. We now have a velocity and an area and can compute the discharge in the edge. Using Q equals AV, the result is Q equals 0.3535 times the user measured length times the ADCP measured depth and the ADCP measured water velocity. For a rectangular section, we know that the velocity will go to 0 at the bank, and the equation by Fulford and Sauer does not capture the no-slip condition at a vertical bank. However, from empirical data, on a smooth concrete wall, a coefficient of 0.91 is commonly applied. SonTek used the data from Rance and others in 1982 and developed the equation shown here to vary the coefficient based on the ratio of edge distance to depth. TRDI averages X and Y velocity components for all bends for 10 valid ensembles and computes the velocity magnitude from this average. TRDI does not consider the top and bottom extrapolations. Only measured cells are used. Based on the direction of flow and the overall cross-section direction, a direction to the mean velocity is assigned as either upstream positive or downstream negative. SonTek uses a more complex approach. They compute a mean X and Y velocity profile using only the edge ensembles. It assumes all ensembles have the same cell size as the first edge ensemble of that edge. If all are invalid, it uses the first valid ensemble. The side lobe cutoff is the mean of the shallowest beam for all of the edge ensembles. Depth is computed as a simple average. Top and bottom extrapolations are computed for the mean x and y profiles. The x and y components of the mean velocity are computed using a depth-weighted average. The velocity magnitude is projected perpendicular to the distance made good rather than parallel to the bank. This projected velocity is then used to compute the edge discharge. Perhaps the most interesting difference between the manufacturer's software is how it handles invalid data. For TRDI, if the bottom track, depth, or water track is invalid, the entire ensemble is marked invalid, and the time between ensembles is extended to the next valid ensemble. Essentially, this is backfilling using all the data from the next valid ensemble. If GPS is invalid, the last valid boat velocity from GPS is used indefinitely until a new valid GPS boat velocity is obtained. For SonTek in River Surveyor Live, if the bottom track is invalid, the last valid boat velocity is used for up to 9 ensembles, after which the boat velocity is set to 0. If the depth is invalid, the last valid depth is held indefinitely until a new valid depth is obtained. River Surveyor Live does not screen water data, so there are no invalid water data. If GPS is invalid, the time between ensembles is extended to the next valid ensemble. Essentially, this is backfilling using all the data from the next valid ensemble. Bad bends, like bad ensembles, are bends where the data processed by the ADCP does not meet quality thresholds, and the velocities may be unreliable and are therefore marked invalid. Bad bends can occur anywhere in the cross-section, but for purposes of estimating the discharge, these invalid bends are categorized into 3 cases. Bad bends can be located adjacent to the unmeasured top zone, in the middle of the profile, or adjacent to the unmeasured bottom zone. The way the discharge is estimated for these cases varies. For bad bends at the top and bad bends at the bottom, we again start with the discharge equation for the top and bottom extrapolation and simply increase the depth of the unmeasured area by increasing dz to account for the bad bend or bends at the top and bottom. How missing bends in the center of the profile are estimated depends on the extrapolation methods selected by the user. If the power fit is selected, the cross product for the missing bends are interpolated using the power fit through the data. Therefore, if this point were bad, it would be interpolated to have this value. If, however, the bottom extrapolation method is set to no slip, a linear interpolation method is used. Therefore, if this point were bad, it would be interpolated to have this value. Thus, how bad bends in the middle of a profile are handled depends on the extrapolation method used for the bottom. Now, let's look at lost ensembles. Lost ensembles are ensembles for which Wind River never received a complete data stream from the ADCP. This is usually caused by communication problems. When this occurs, you only see a blank spot on the contour plot. To explain why and what Wind River does to estimate the discharge, we begin with the discharge equation. When an ensemble is lost, the time for the ensemble is unknown. So Wind River assumes that the next good ensemble had a longer duration. dt becomes larger because it is computed as the time difference between the last and current ensembles. Therefore, the discharge for lost ensembles is computed backward from the next good ensemble. It is possible for TRDI ADCPs to have valid beam depths but not have valid bottom track as shown in the example on the left. TRDI also requires at least 3 beams have valid depths or the depth is reported as invalid. In both situations, the dt is increased and the discharge is computed based on the next valid ensemble, including the water, depth, and boat speed from that ensemble. SonTek provides the capability of using composite tracks. When composite tracks are on and bottom track is primary, invalid bottom track is replaced with VTG or GGA. When GGA is primary, invalid GGA are replaced with VTG or bottom track. When VTG is primary, invalid VTG are replaced with GGA or bottom track. The graph shows the water profiling code on the right axis and the track reference code on the left axis. The track reference code is oscillating between 4 for VTG and 2 for 1 MHz bottom track. When using composite tracks, beware of what is happening. With composite tracks on, it looks as if we have good bottom track for the entire transect. However, if composite tracks are turned off, we see the bottom track actually had problems. When using composite tracks, the use of the bottom track reference code graph is recommended because just using the ship track can hide problems in the primary reference. SonTek automatically uses composite depths. If the preferred depth, either the vertical beam or the 4-beam average, is invalid, the other is automatically used if valid. If both depth references are invalid, the last valid depth is used indefinitely or until a new valid depth is measured. In this example, the depth was invalid for sample 76, so the value for sample 75 was used. Likewise, the depth for samples 78 and 79 were invalid, and the depth from sample 77 was used. What you don't know can hurt you. This is the primary reason for discussing how ADCP measures the Doppler shift, the various modes of operation, and how the software processes the data. Previously, I told you that for SonTek, if bottom track is invalid, the last valid value is held for 9 samples and then set to 0. Looking at the color contour plot, there doesn't appear to be any major issues with this transect. However, if we look at the track reference code graph, we see that from sample about 20 to 140, the bottom track was invalid. Looking in the samples table, we see that the boat speed is 0 and the discharge doesn't change. However, this cannot be seen in the contour graph. So what velocity is plotted for samples 20 to 140? It is the raw relative velocity with 0 correction for the boat speed because the boat speed has been set to 0. Likewise, because the boat speed is 0, the computation of discharge using the cross product results in a 0 discharge, thus no change in the total discharge. If you could process the same data in both River Surveyor Live and Wind River 2, you would get different discharges due to the differences in how various situations are handled. That concludes our discussion of computing discharge and the different approaches used by the manufacturers and the consequences of those approaches.